Yesterday we spent a lot of the class working on wave behavior. Okay, so remember that some things you need to go over and have committed to memory are things like what happens to a wave when it encounters a boundary. Some of it is transmitted, some of it is reflected. Okay, the nature of that reflection and transmission based on whether it is going into a less dense, faster, or more dense, slower material. Okay, remember that if it is going from less dense to more dense, from fast to slow, the reflection will be inverted. Okay, and if it's going the other way, okay, from slow to fast or more dense to less dense, that the reflection will be upright. Okay, other things obviously to look for are what the wave looks like in the new medium. Is it longer or is it shorter? Has it traveled further than the reflected wave or not as far as the reflected wave? All of those things are things that can tell you the nature of the second medium. Just wait outside, please. Okay, so remember that that's what we went over. Those are things you need to commit to memory because there will definitely be some visual-based questions on the unit exam from that. Okay, so we started standing waves yesterday. I just kind of got through showing you the Tacoma Narrows Bridge thing, and I kind of explained how it took them like 50 years to figure out why the thing had collapsed, which should have been not reassuring at all if you were driving over the new version of it. Okay, but they did figure out how to keep it from collapsing, just not why exactly that occurred. Okay, so fair amount of engineering and physics that goes into that type of design. So today we're going to continue talking about standing waves. Okay, I showed you some of those on the spring there yesterday. Okay, we're going to look at those, and we're going to move into air columns, and I've brought one with me. Okay, so we'll do a little demo with the air column here. Okay, you've all made music with air columns at some point in your life. Okay, so if you haven't already found the notes, please find those. Okay, and we'll get started here in like less than a minute. Okay, so the thing to remember about standing waves is that they don't stand still. The pattern of interference created by waves traveling back and forth in the medium is what stands still. Okay, there are going to be areas where there's constructive interference. We saw those yesterday, the areas where the spring moved a lot, okay, and areas of destructive interference where the spring barely moved at all. Okay, remember that we see that big amplitude because all of those waves are identical. They have the same frequency, the same wavelength, and they're on the same medium, so they're traveling at the same speed. So they cannot help but meet up and interfere constructively in one place and destructively in the other based on their length, frequency, and speed. Okay, so you only get a standing wave pattern if you have all the waves being the same. Okay, if I was randomly generating waves, it would have just been a jumbled mess. Okay? All right, so understand that standing waves result from repeating patterns of interference. The standing wave is not a wave standing still, it is an interference pattern. Okay? Look at how those patterns are formed. Okay, we kind of saw that a little bit in the Tacoma Narrows video. You could see the wave coming in at the stanchion. Okay, so it had a stanchion at either end, and then there was the bridge in the middle. And you could actually see that when the wave was coming in like that, okay, that almost immediately after, the next thing we saw was the bridge looked like this. Okay, that it was flipped, because that stanchion was acting as the fixed end, okay, the more dense medium that wave was reflecting off of. Okay, so it was always creating its exact opposite at each end, right? And obviously those waves just kept getting put into the bridge until it was, going like crazy, and then it finally fell down. Right, so we're going to kind of look at that. Okay, the reason we see that pattern happening is because reflections off that end always produce the opposite. They always reflect inverted. Okay, ringing a bell from yesterday? Okay, so we did this yesterday at the front of the room. Okay, I made these three, and actually the fourth one too. Okay, but then I started getting sweaty because it was too much work. Okay, to make those patterns of interference. Right, all standing waves work the same way. There's the first interference pattern, the second, the third, the fourth, and if you can get a generator that can keep generating faster and faster waves, you'll just keep getting smaller and smaller wavelengths, okay, and more of those patterns on the medium. Okay, everybody with me so far? Okay. So the first pattern is what we call the fundamental frequency. Okay? It is the first frequency that produces a standing wave. Right? And that standing wave has one area of constructive interference right smack in the middle and two areas of destructive interference at either end. Right? So that first pattern is the fundamental frequency. Okay? Which we usually just label as F1. Okay. Now, yesterday when Beckett and I were making the waves at the front, okay, I said, okay, I'm making this first pattern and I'm making it at a frequency of 1 hertz. And then I asked you, what is it going to look like if I shake the spring at 2 hertz? Okay, and we got this second pattern, right? So this, okay, is our second harmonic. Okay, and it is F2. It is 2 times the fundamental. And every frequency that produces a standing wave after that is a multiple of the first. Okay, that's why I said, what if I shake it at 2 hertz? And then at 3 hertz? It's a multiple of the first. I couldn't just pick any random frequency and get those wave patterns to show up. They were multiples of the first one. Okay, so second harmonic, third harmonic, okay, and that would obviously keep going. Okay, you just get more and more kind of waves. Okay, now, what do you notice about the numbers? How many areas of constructive interference does F1 have? Right? F2 has 2. Okay? So it's easy to remember, right? You can look at a wave pattern and go, oh, that's the fundamental frequency, or that's the second harmonic, that's F2, that's F3. You just have to look at how many areas of constructive interference are there, and it's easy to remember. Now, here's something I might ask you that involves you understanding not just the harmonics, but also a little bit of the stuff we did earlier in the unit about wavelength. If I asked you, this string, okay, that they're making the waves on, this string is 6 meters long. What's the wavelength for the fundamental frequency? See, that's trickier, right? Because we got to integrate it with something we learned earlier. How many wavelengths are on that string right now? That's tougher. Okay. A full cycle is 1 wavelength, right? That would look like this. That would be 1 full cycle, right? So if I completed the pattern, how many wavelengths are here? Half. Yeah, there's half a wavelength here. So the actual wavelength isn't 6 meters, it's 12. What's the wavelength for this one? Adam, what's the wavelength for this one?
1.
Okay, so there's 1 wavelength on here. This is 6 meters long. What's the wavelength?
6.
6 meters. Okay, how many wavelengths are here? Mary, how many wavelengths are here? 1.5. 1.5. Okay, so that would make this wavelength 4 meters, right? 6 divided by 1.5. Okay, everyone following me there? That is easily the kind of thing I could diagrammatically ask on a unit exam. Okay, here's a standing wave pattern. Okay, the string that the waves are on is 6 meters long. Okay, then I'd ask you, what's the speed of the waves? So you'd have to go and calculate the wavelength based on the visual information you're getting here, and that's 6 meters, and then you'd have to use the universal wave equation after that. Right? Then you'd go, okay, well, V equals F times lambda. I would have, of course, had to tell you what frequency the string was being shaken at, and you'd be able to get the speed from there. Okay? You see how this all comes together? And why we call that the universal wave equation? I mean, we're using it for everything going forward. Okay? Questions there? Okay. Do we ever see in a string instrument these two waves. If you pluck a guitar string or violin or anything like that, do you ever get anything other than this? No. It'd be pretty wacky to see a guitar string have a node, okay, that's an area of destructive interference, in the middle of it. When you pluck it, you just get this. So on a guitar, or any string instrument, how do you change the sound that it makes? Who in here plays a string instrument? Maybe I should ask that first. Okay, so how do you make it make a higher pitched sound?
Just move like where the tension is on the string.
Right, yeah, where you pinch the string against the bridge, fret. Okay, I always get it wrong because I'm not a music guy. The only instrument I can play is my MP3 player. Okay, so if you pinch the string against the fret, okay, you only let that much of it vibrate. Okay, that short wavelength is going to produce a high frequency of sound. If you go higher up the fret, now you're letting more of the string vibrate, and you're going to get a lower frequency because you have a longer wavelength. Okay, so the standing waves are being used to produce different frequencies of sound. Okay, with me so far? Okay. All right, so terminology here. Areas of constructive interference, areas of destructive interference. Okay, in a standing wave pattern, the areas of constructive interference are called antinodes. And areas of destructive interference are nodes. Okay, nothing fancy about the names. Okay, node literally means no movement. And to make sure you've got that one written down, because I will use those terms, nodes and antinodes, on quizzes and tests. So you've got to know what they mean. All right, questions so far? Okay, so we've covered that standing waves can come in a fundamental frequency with one antinode, okay, and then the harmonic frequencies after that, F2 would have two antinodes, F3, the third harmonic, would have three, and so on and so on. Okay, so that's the stuff we have to know about kind of the nature of or appearance of standing waves, okay, those terms and those pictures in our mind. Okay, this slide, same thing. We're just talking about the antinodes here. Okay, so antinodes are areas of constructive interference. Okay, and as we said before, okay, the term we use for the first standing wave pattern that will form on the medium is the fundamental frequency. Okay, the second one is the second harmonic frequency. So the next one in line, okay, the next frequency. Incidentally, in music, this is how you produce different octaves. Okay, so if you're like looking at a piano, okay, inside the or on the keys, there are how many C's? I don't even know. There's like 4. I suppose it depends what kind of piano you have. Okay, so there's 4 keys, let's say, along the piano that are C. Okay, there'd be the lowest C, then there'd be like middle C, and okay, maybe there's only D then. Okay, there'd be like the third C, which would be the higher one. Right? If you ever open up a piano, like a grand piano, and look inside, what you see is that shape that all kind of grand pianos have, right? Like they kind of go like this. Okay? The reason they have that shape is because the strings that are attached to the keys get longer and longer and longer. Okay, so anytime you press a key, there's a little thing that strikes that string and sets it oscillating back and forth. Okay, so this would be like high C, that would be F3. Okay, this would be like middle C, that would be F2, and this would be the low C, that would be F1. It would have the longest string and thus the longest wavelength. Okay, you probably thought that grand pianos just had that shape because it looked cool, but it's actually functional. Okay, the strings get longer. Inside a regular like square piano, they're just arranged vertically instead of horizontal. Okay, questions on the nature of those? Okay. All right, so each standing wave pattern, like we said, okay, is a multiple of the first. Okay, now don't worry about the words, the overtones here. We don't use those, neither do they on like a diploma exam or anything like that because they're confusing, the numbers don't match. Okay, so we go with first harmonic, fundamental, okay, second harmonic, okay, F2, third harmonic, F3, because those make a lot more sense given the structure of the wave. Okay, everybody's good with that? All right, so we talked about the Tacoma Narrows stuff there yesterday, okay? And on the Tacoma Narrows Bridge, from what we saw, how many wavelengths were on the bridge? Anybody remember? How many areas on the bridge were like twisting massively? Yeah, there's one full wavelength on the Tacoma Narrows Bridge. It was never designed to oscillate beyond its fundamental frequency. Okay? It was designed just to do this. Up and down. That's all it was designed to do at its fundamental frequency. Nobody ever thought of the situation that occurred over those days where the wind just blew across it, okay, and got it to oscillate in not just an up and down fashion, but in a like three-dimensional wave, okay, where there was a torsional wave as well as an oscillating wave. Okay, and there was more than half a wavelength. There was a full wavelength on the bridge, which meant in the middle, where there was no support at all, that thing was doing this, which is of course why it broke there. Okay. All right. Now we talked about how we fixed that. Okay, or how they fixed it. They just made sure that what couldn't happen on either side. What did they do with the cables?
The frequencies wouldn't match?
Right, they made sure the frequencies wouldn't match by changing the tension in the cables on either side. Because what controls the speed of a wave?
The density of the medium?
Yeah, the nature of the medium. Could be density, could be tension, okay, all that kind of stuff. Lots of things. Any property of the medium. When we're talking about water, it could even be depth. For air, it can be temperature. Okay, so any property of the medium that changes, okay, is going to change the speed at which the waves can travel. So if they make the cable on one side tighter, the waves travel faster on that side than they do on the other. Then you can never have the waves make a standing wave pattern because they don't ever match. The problem with the Tacoma Narrows Bridge originally was the tensions were identical and waves could travel on both sides of the bridge at the same speed and resonate. It's the resonance that's the big problem. Okay? If you get it to resonate, you're in real trouble. Okay, now, got these pictures here. I took these when I was in New York just before Christmas. Okay, these are called pencil skyscrapers. Okay, they're building a lot of these. The New Yorkers do not like them. Right? They think they're an eyesore. They're kind of right. Okay, they're just ridiculously tall skyscrapers. Okay, and very, very thin. What's the problem if you've got a lot of length and not a lot of like girth? How strong are you? Like if you're a really tall tree, but you're not very big around, are you going to blow over in the wind? Absolutely. Okay. Well, that's the problem with these. New York can get really big winds blowing off the ocean. So these buildings have to be designed so that they flex and they sway a little bit. Okay? Even the buildings in downtown Calgary, which are not skyscrapers. Okay? Like I remember when I was a kid, I used to think that these were, the Calgary Tower was a skyscraper. That doesn't even go halfway up one of these. Okay? Like it's mind-boggling to think how tall some of these places are. Okay? So these buildings are very tall, but they're very thin, and they're designed to flex in the wind. If you just build them rigid, they'll break. Okay, you never want to build a building or any structure so that it's completely rigid. It's got to have some flex. Now, you'll see halfway up this one, there's a gap. Okay, there's a gap here in this one, there's a gap here in this one, and a little further down inside the tree, there's another gap. Okay, what they do with those gaps is, obviously first, the wind can blow through there. Okay, which means the wind can't push on the whole side of the building. Okay? Does that interrupt and change the forces that can push on it? Okay? It does, and then they're not uniform. But it also changes the nature of each section of the building. So any wave that starts to travel through the building travels at a different speed in this section than it does in this section. Which means you can never get a resonating wave okay? That'll start to make that thing go like this and fall over. Here's the problem. Every one of these pencil skyscrapers has a multi-million-dollar penthouse apartment that no one will buy. Okay, it's a major real estate problem. No one will buy what would seem to be the best piece of property in these buildings, because you get seasick if you live in it. The building sways so much that people get sick in the apartments in the wind. And the elevators won't go all the way to the top floor because they'll get jammed in the elevator shaft while the building flexes. Nobody wants to pay millions of dollars for an apartment they have to take the stairs to. And we're not talking about a small number of stairs either. Okay? So in both of these skyscrapers, the maximum height of the elevator in a wind of more than 30 miles an hour is right there. After that, it will automatically shut off and not allow the elevator to go to the top, and you get to take the stairs that are swaying, mind you, while you're climbing them. Okay, so they're having a little trouble, as you can imagine, selling those properties. Okay? You can even feel this in downtown Calgary. If we're getting a Chinook and you're in one of the tall buildings downtown, you can feel the sway. And my wife used to work in one of those towers, and she's like, yeah, there were days when it was, you know, blowing 100 kilometers an hour that people were like taking Dramamine to stay at work. There was enough motion that they could sense it. Not enough that the building's gonna fall over, it's designed to flex. Okay? Would the same thing be true in an earthquake-prone area? Could an earthquake cause waves to travel through the building? Yeah. So in earthquake-prone areas like Los Angeles, what they'll do is the footings, okay, in Alberta and other places, footings are just holes that are drilled really deep into the ground below the frost line and filled with concrete, and then they're attached to the building. So that makes the building super stable because it essentially makes it go deep into the ground. In an earthquake-prone area, they build them on springs. Okay, those footings have springs in them. I'm not talking like the spring in your pen either, okay, or even the spring in your car. We're talking massive shock absorbers, okay? And on every corner of the building, the shock absorber has a different tension, okay? That way, when the earthquake starts to shake the building, it can't resonate. The waves travel differently because they're dampened on different corners of the building, okay? There's all kinds of simple wave physics that goes into the design of really tall structures. Okay? Making sense? Okay, so we were talking about this earlier, okay? Why do we always have a node at the two ends of the standing wave? Okay, because each end of the standing wave is a fixed end, an infinitely dense medium, okay? And the wave is going to reflect off of that point, and it's going to reflect, John? Invert. Okay, it's always going to reflect inverted, so it's going to come. If it goes in as a crest, it's coming back as a trough. It's always producing its exact opposite there. Okay, so you always get a node at either end. Okay, and that's all this diagram is showing. Okay, all right. I'm going to give you 2 minutes to absorb that. Okay, and then we're going to start talking more about like musical instruments and standing waves. Okay, so just take 2 minutes, take a couple breaths here, and then we'll move on. Yeah, just leave your phone. Okay. Okay, while you're decompressing, don't forget, okay, June 13th, last day to hand in overdue assignments if you want them graded, okay, and the mock final sign-up will come out later that day, okay. Remember, that's optional, you don't have to write it, but if you want to, you just sign up for what time, okay, and the times are here, June 18th in the morning, June 18th in the afternoon, or June 20th in the morning, okay. focus back up here again, guys. Okay, and we'll move on to, okay, our musical instrument stuff here that we were talking about just a minute ago. All right, so with the guitar situation, violin, string instrument of any kind, okay, the way you make different frequencies of sound is you change the wavelength of the string that is vibrating. Okay, so you pinch it against the fret in a different position, okay, it produces a longer or a shorter wavelength, and that is going to produce a different frequency. Okay, now, before, what did we say could never change? Frequency could never change. Am I saying something that goes against that? I'm saying if you change the wavelength, you can change the frequency. Is that violating that rule at all? Sometimes it kind of seems like it, but it's not. The frequency is controlled by the source. The string is the source. If I change the source, I change the frequency. Remember, the rule for frequency never changes is once a wave is produced, the frequency never changes. I'm making new waves with a different frequency by changing the source. Okay, so sometimes people get a little bit stumbled on that. Okay, because they're like, well, you said frequency can't change. That is 100% true. Once the wave is produced, its frequency will never change. All I'm doing is changing the source and making different waves with a different frequency. Okay. All right, so if we're looking at this here, okay, we've got a 60 centimeter string that is oscillating. What's the wavelength of this wave? Okay. 120 centimeters, right? Because that's only half of a wavelength. A full wave would have another antinode after that. Okay, so the wavelength here is 1.20 meters. And it's making a frequency of 165 hertz. I mentioned this before. Could I give you a picture like that with that information and ask you for the speed of the waves? Okay? 100%, how would you get it? Virginia, how would I get it?
Lambda times frequency?
Yep, yeah. V equals F times lambda, right? It just comes back to the universal wave equation. Okay, 1.2 times 165, okay, going to give me, what about 340? Somewhere in there? Sorry guys, I should have started my calculator before. That's a bad estimate, it's nowhere near that number. Okay, 1.2.
Can I just get these two guesses? When you're finished with this, take a figure.
Yes.
Okay.
Okay, so the speed of those waves would be 198 meters per second. That's not the sound waves, those are traveling in air. That's the speed of the waves on the guitar string. Okay. All right, in that second situation, I'm using less of the string, so my wavelength has decreased. Speed's still the same, but now I'm producing a higher frequency. Okay, so the shorter the wavelength, the higher the frequency is going to be when you're playing an instrument. Okay, that includes wind instruments, which is what we're going to talk about next. Okay, wind instruments still use standing waves. They just use a vibrating column of air. Okay, so a wind instrument of any kind is going to make a column of air oscillate, okay, and produce like a humming, okay, sound of various frequencies. Okay, anybody ever blow across the top of a bottle? Okay, that's a simple air column. Okay, so, oh, I'm terrible at it though. Okay, I'm going to do a better air column because I brought one with me, but I'm terrible at that. But yeah, if this right now, this is empty, right? This would produce the lowest frequency of waves. If I filled it higher, like half full, would it produce a higher or lower frequency? Higher, because the wavelength would be shorter, right? The wavelength can only be the length of the column of air. Okay, that's what we're going to talk about next. And put air demo fails miserably. Okay. All right, so wind instruments, like we said, are going to cause vibrations either from the lips. So if you play like a brass instrument, okay, so like the trumpet or the tuba or the trombone or any of those, okay, it's the lips that are producing the vibration. Have you ever, how many people in here play a brass instrument? Okay, nobody, all right. So what you have to do with a brass instrument, this is why they all have a spit valve, which I think is disgusting, but you have to make your lips do this inside the instrument. I'm going to face away from you because otherwise it'll be really gross. Okay? You got to do that, and your lips have got to like do this thing inside the instrument. Okay? And depending on the size of the instrument, you can produce different wavelengths of sound. A trumpet is really short, so it generally produces higher frequencies. It's why an orchestra doesn't just have trumpets. Okay? It has trumpets, it has trombones, and it has tubas. Okay? Tubas are really big, so they make much lower frequencies because they make way longer wavelengths. Okay? Making some sense there? All right. Now, there are two types of air columns, open and closed. Okay? Closed air columns are like this bottle. They are closed at one end. Okay? Open air columns are open at both ends. So most wind instruments are open air columns. Okay? Open air columns produce a wider range of sound. Okay? Closed air columns can only resonate at half of the frequencies that an open air column could resonate at. Okay, so instruments that would be a closed air column, drums. Okay, drums are a closed air column. The skin represents the closed end and the open end is the other end. Okay, and you get that column inside vibrating, okay, and producing the sounds. Okay, whenever you strike the skin of the drum, okay, the skin vibrates and makes the column of air below it vibrate. Okay. Now, anyone ever watched someone play like kind of like, was it like they're like a bongo, right, where you use both hands on it? They have different sizes of them, right? The longer they are, the lower the frequency. But you can produce different frequencies of sound on those drums depending on where you hit the skin, and also, if you have many of them, how big around they are and how long the tube is. Okay? If you hit more towards the edge, you're getting the full skin to vibrate. If you hit more in the middle, you're producing a slightly shorter wave. Okay, so you can make different sounds. That way, a cajon kind of works that way as well. Okay? All right, so open and closed air columns are going to make columns of air vibrate. Now remember, sound is a longitudinal wave. So it's a compression and a rarefaction, okay, going together. We don't actually see the longitudinal waves. But what we do is we draw them like they're a transverse wave because those are easier to visualize. Okay? Now, for a closed air column, the first time we get a sound in the closed air column, it's going to look like this. Okay? We're going to get that much of a wave in the tube. Okay? So this is the start of the wave, this is the end of it. Okay? So a full wave looks like this. Okay? How much of the wave is actually in the tube? Okay, here's the start of the wave, and this is where the tube ends, so that's the end of the wave. How much of a wavelength is in the tube? A quarter. Okay, there's 1/4 of a wave in the tube. Now, here's the thing with air columns. They only make sound if there's an antinode at the openings. Or if it's closed air column, opening, because there's only one opening. Okay? They only make loud sounds when there's an antinode at the top. Okay? What if there's a node at the top? What if I had a closed air column and the wave inside looked like that instead? What would I hear? A node is a place where what kind of interference occurs? Destructive. What do you hear when there's destructive interference? Nothing. Okay, so I'm going to demo that for you here with my handy dandy closed air column, which is going to make a horrible mess on the floor. Okay, what'd you notice about the frequency of sound it was making as I filled it up? Got higher and higher, right? That column of air got shorter and shorter and shorter. Okay, so here's what we're going to do. I'm going to use this tuning fork, which is G. What's the frequency of G? I thought you band people might know that. G is 392 hertz. I only know that because it's carved on the tuning fork. I would never know that otherwise. Okay, so this tuning fork makes a frequency of 392 hertz. Okay, here's what we're going to do. Okay, and I'm going to need somebody's help here. Maybe I'll get Nick's help. Okay, I'm going to want you to read the length of the tube wherever the water line is when I stop. Okay.
Is that 21?
21, exactly.
Little under 21.
A little under 21? Okay, I'm going to move a little closer to it so we can get this accuracy actually doesn't matter for what we're doing here.
It's like 21 and a quarter.
Okay, 21.25. Okay. Okay, so the first time we got this thing to resonate, okay, and that's what it was doing, that's why the sound suddenly got louder, I found an antinode. Okay, that was the first antinode that was at the top of the open end of this closed air column. Why is this a closed air column? Can any sound get out the bottom? Okay, it's going to reflect off the water, right? The water acts as a closed end. Okay, all this thing is doing is acting as that column of air, and because it's got the graduations on it, we can tell how long the air column is. All right, so we heard the first antinode. Okay, listen to see if you can hear the first node. Okay, like all you can hear is the tuning fork itself. It's not resonating at all, right? It wasn't making any noise there. What's it reading there, right?
Like 65.
Awesome. Okay, it's working out perfect. You don't know why yet, but it's working out perfect. Okay. Okay, 0.65 meters. What's it reading there?
109 and a half.
109 and a half? Okay, that should be close. Okay, so obviously there were times where this thing resonated. That's an antinode at the top. Okay, all of those mark the antinodes that we could find. Okay, so the first antinode represents how many wavelengths in the tube? When I diagrammed it there, the one in the middle, how many wavelengths were in the tube? 1/4. Okay. Okay, so that means that this represents 1/4 of a wavelength. Agreed? Okay, so if I multiply that number by 4, will that give me the wavelength? All right, so the wavelength of that sound is 0.85 meters. Okay, then we got another antinode here. The wavelength should be the same because I was using the same tuning fork, agreed? So does that mean there was a different looking wave in the tube? Or there was more of a wavelength in the tube then? Yeah, the second time we heard a sound, okay, what we were actually hearing was this situation. How many wavelengths are in the tube? Three-quarters. Okay? Because the antinodes would be half a wavelength apart. Right? If we're looking at this diagram here, that's one antinode, that's another antinode. They're half a wavelength apart. Okay? So this would be 3/4 of a wavelength. So this number equals 3/4 of lambda. Okay? So if I divide that number by 3/4, okay, 0.75, I should get that. Oh, 0.75. Is that pretty close? I mean, within our margins, right? Like I'm trying to judge, is this the loudest or was it loudest a little bit further down? Like it's pretty close for the way we were measuring that. Okay, so 0.87, we'll say. Okay, and then we got another one at 1.09. So if this was 1/4, this is 3/4, this should be how many quarters? 1, 3, what's next in the pattern? 5, right? Another half a wavelength away, right? If I draw another half a wavelength on here, okay, it would look like that. So we would have 1/4, 3/4, 5/4. Okay, so that represents 1.25 wavelengths. Okay, so if I divide that number by 1.25, pretty close, right? We got 0.87 twice, okay, the way we were judging that. Okay, there's a fair amount of human error in that. Okay, let's say that one, I didn't do a very good job of guessing where it was. Let's say our wavelength is 0.87 meters. Calculate for me right now, and this shouldn't take you more than 30 seconds, the speed of sound in this room. Remember that was 392 hertz that I was using for the tuning fork. Yeah, leave your phone, please. Okay, what do we get? All right, if I want to calculate speed of sound, V equals F times lambda, 392 hertz times 0.87. (341 meters per second). Okay? Given that it's probably about 20 degrees in here, that's not too bad. We are at altitude, that does affect it a little bit. Okay? But that is right about what the speed of sound should be. Okay? Is that totally the type of thing I could ask on a unit exam? that doesn't really require any special knowledge other than being able to go, okay, how many wavelengths are in the tube? Okay, if I know how long the tube is, I can calculate the wavelength, and then from there, I can calculate the speed. Okay, or I could give you the speed and ask you what frequency was being used. It all still comes back to the universal wave equation. There's just tons of applications of it. Okay? This is also why, okay, you have to continually tune an instrument. Okay? Like especially a guitar or string instrument. Okay? Temperature can obviously affect how much tension is in the strings, but air temperature can affect the speed of the waves. And if I'm perceiving waves to be traveling slower, I might also perceive them to have a different frequency than they would have had somewhere else. And so each time I go to a different place, I have to retune the guitar, okay, or string instrument or whatever. Okay? Everybody with me on that? Okay. Okay, so closed air columns, okay? That's the ones we're going to look at first here. That's what we just did, okay? Closed air columns, okay, are closed at one end, okay? And they only resonate when there's an antinode at the top, okay? The first sound you hear is the fundamental frequency of that tube, okay? And that first antinode is 1/4 of the wavelength. So there's a special formula that we use for closed air columns. Okay? And it is that lambda equals 4 times the length of the tube at F1. Okay, and we know that because for any closed air column, the first resonant point is at 1/4 of a wavelength. Okay, so the tube is 1/4 of a wavelength long. So if I multiply the length of the tube by 4, I've got the wavelength, which is exactly what I did, okay, just a minute ago. Okay. Now, the second sound you could get in an air column, okay, if I kept the column the same length, I'd have to keep switching tuning forks before I would get another one to resonate. Okay, the next time it would resonate, it would be at 3/4 of a wavelength, and then at 5/4, and then at 7/4, and so on. Okay, that would mean it resonates at F1, F3, F5, F7, 9, 11. Okay, closed air columns don't resonate, that is, make sound, at odd numbered frequencies. They only make sound at odd numbered frequencies. They don't resonate at even numbered frequencies. Why? What's at the top of the tube at F2, F4, F6, and F8? Notice they're not drawn.
A node.
A node. Okay? This is what F1 looks like. It's an antinode. Okay? If I drew F2 on here, okay, so if I just had like it in the middle here, F2 looks like this. There's half a wavelength in the tube, but there's a node at the top. There's a standing wave in the tube, but you can't hear it because there's an area of destructive interference at the top. Okay? This is why closed air columns are less commonly used as musical instruments. They don't produce as wide a range of sounds because they can only resonate at odd numbered frequencies. Okay? Open air columns resonate at all. F1, F2, F3, they always have antinodes at either end. Okay, so here's how a question like this could go. Okay, I tell you the air temperature in this room where somebody's blowing across the top of a bottle is 20 degrees Celsius, so you can calculate the speed of sound. And I tell you that the bottle is 20 centimeters tall and half full of water. Why is the half full of water an important detail? Beckett?
Short since overall.
Right. Then that means the column of air is only how long? 10 centimeters, okay? Little details like that gotta watch for. We're talking about a resonating column of air, not water, okay? Water would be reflective, just like it was here, okay? So, I would tell you this, I would give you the ability to calculate the speed of sound, and I would tell you how long the air column was, okay? Could you calculate the frequency of sound it was producing? You could, because if you know the length of the tube, you can calculate the wavelength being produced. Since I gave you the ability to calculate the speed, we're right back to this. You would know lambda, you would know v, and you could calculate the frequency being produced. Okay? Nothing mathematically difficult, but you have to understand what the waves look like, okay? And the nature of waves themselves to get to the universal wave equation. Now, here's what I might ask as a part B. You've just calculated the fundamental frequency. I would ask you, what's the next frequency you would hear in that air column? So let's say you calculated it and it was 100 hertz. What's the next frequency you would hear from that column of air? Okay, that's trickier. So this is the first one you heard, F1. Okay, the next one you would hear would be F3, because F2 is a node. It doesn't make any noise. F3 is the next one that makes noise. If F1 was 100, what's F3? We talked about this at the beginning. The harmonics are multiples of the fundamental. So if F1 is 100, F3 is 300. It's a multiple of the first. F3 is 3 times bigger than F1. Okay, so the next frequency you would hear for this one would be F3, 300 hertz. Okay, that requires, again, that understanding of resonance and what columns can resonate. Yeah, just leave your phone, please.
Can I go after you?
Yeah. All right, questions there? Okay, we're going to work on this today, guys. Don't worry. This is not like I'm going to teach you this once and we're going to walk away from it. Okay, we're going to spend time working on these kind of problems. Okay, so the other kind of air column are open air columns. So they're open at both ends. Okay. They resonate at all frequencies. F1, F2, F3, F4, all of them make a sound. Okay? Because for an open air column, the waves reflect off the inside of the tube. There's nothing to reflect off of at the ends, it's open. Okay? So the reflection actually happens inside the tube. Okay? And so what we get is the first sound we hear in an open air column has this waveform in it. How many wavelengths is this? Okay, remember, one full wavelength of a standing wave looks like this. How many wavelengths are in the tube here? Asha, how many? Not quite. Okay, let's just have a look at this. If I take this and superimpose it on here, okay, I've got a node in the middle, and I've got an antinode and an antinode. Okay? This is 1/4, 1/4, 1/4, 1/4. How much of the wavelength is in there? Half. Right? It's between 1/4 and 3/4 that are in the tube. Okay? There's an antinode at each end. Okay? Antinodes are half a wavelength apart. And if there are two of them in there, then there's half a wavelength in the tube. Okay? How many wavelengths in this one? That's a quarter, a quarter, a quarter, a quarter. How many wavelengths are in there? One. Okay?
I forgot my phone.
Okay, does that make sense? Okay, we got to be able to look at a waveform and go, how many wavelengths is that? Okay, that's just wave structure. Okay, doesn't always lay out quite the way we would imagine it. Right? Okay, so for an open air column, the first sound we hear has half a wavelength in the tube. That means if I multiply the length of the tube by 2, because there's half in there, then I'll have the wavelength. Okay, so for an open air column, lambda is 2L at the fundamental frequency. Those two formulas, lambda is 4L, lambda is 2L, are on your formula sheet. Okay, what you have to know is which one goes with which type of air column. Okay, so closed air columns have a quarter of a wavelength, so they go with 4L. Okay, open air columns have half a wavelength, so they go with 2L. Okay, and as we said, they resonate at all frequencies. Okay, so this is F1. Okay, here's half a wavelength in the tube. This is F2. There's a full wavelength in the tube. This is F3. There's a wavelength and a half in the tube. This is F4. There's 2 full wavelengths in the tube. Okay. You're never going to be asked to memorize how many wavelengths are in the tube at F2, 3, or 4. Okay? You have the formulas that deal with the fundamental frequency. That's what we'll deal with. Okay, I want you guys to copy that one down, and we're going to walk through it here in a minute as an example. Okay, so let's have a look at this one here. I have a closed air column, and it's resonating at a fundamental frequency of 256 hertz. So they told me 2 things. They told me this formula applies because it was a closed air column. Okay, so as soon as I see closed, I go lambda equals 4L. And they told me its fundamental frequency, F1, is 256 hertz. Okay, what is the length of this air column if the speed of the sound wave is 343 meters per second? So they also gave me V. I have V and I have F. What can I calculate? Josh, what can I calculate if I have V and F?
Lambda.
Right, okay, so I want to calculate lambda. So V equals F times lambda, so V over F will give me lambda 343, okay, divided by 256 hertz. Okay, so 343 divided by 256. Okay, so the wavelength of that sound is 1.34 meters. Okay, that's the wavelength. They want to know how long the air column is. Okay, so they're asking me for this. At F1, there's only 1/4 of the wavelength in the tube. So what do I do with that number? Yeah, what do I do with that number if I want to get the length? Divide it by 4, right? I'm just manipulating lambda equals 4L. I know lambda, so all I have to do is divide it by 4 if there's 1/4 of a wavelength in the tube. Okay, so lambda over 4 will equal the length of the tube. Okay. That's 0.335 meters, or 3.35 times 10 to the minus 1 meters. Okay? There's only so many variations of an air column question I can give you. I can give you the speed and the frequency and ask you for the length of the tube. I can give you the length of the tube and the speed of sound and ask you for the frequency that's being produced. Okay? It's going to be frequency, length, or speed. Those are the only things you can calculate with an air column question, because that's all that's in the universal wave equation, which is what they come down to in the end. Okay? Oh, that's terrible luck. Okay, write that one down anyway. Okay? And we'll go, and I want you to try it. Yeah, sleep your phone. Okay, what's different about this one? Is what? It's an open air column, right? Okay, so an opened air column resonates. Okay, so lambda equals 2L for this one. Okay, and it's the same fundamental frequency as the last one, 256 hertz. Okay, what's the length of the air column if the speed of sound is 341 meters per second? So I'm looking for L. So it's basically the same method as the last question. I have V and I have F. So lambda equals V over F. Okay, 341. Okay, divided by 256. Okay, so 1.33 meters is our wavelength. Okay, and we want to know L. Well, lambda equals 2L, so lambda over 2 should tell me the length of the tube, because at the fundamental frequency, an open air column has this wave pattern, which is half a wavelength, resonating inside of it. Okay, so our 1.33 over 2 is unfortunately going to give us 0.666 meters. That's pretty bad luck, but okay, that's what it came out to. Okay, all right, making sense there? Okay, how many people have their workbook printed? That's what I thought. Okay, I'm going to put it up on the board here, and I'm going to put the worksheet up. We've done 1 and 8 on the worksheet. What I want you to do is go back and forth between the closed air columns, that's questions 2 to 7, and the open air columns, that's questions 8 to whatever it goes to on the sheet. All right, so for number 2 here, we have a closed air column. So right away, as soon as we see closed, lambda equals 4L. Okay, its fundamental frequency is 440 hertz. Okay, we're looking for the speed of the sound waves. Since I know the length of the column, okay, they told me it's 18.9 centimeters, so length is 0.189 meters. It does have to be in meters. Okay, I can calculate the wavelength. So lambda is just going to be 4 times that number. All right, so there's my wavelength, 0.756 meters. All right, now that I've got lambda and F, V equals F times lambda, 440 hertz times 0.756. Okay, and I'll get 333 meters per second. Okay, there's really not much to air columns in terms of the math. Right? There is a fair amount in terms of the visualization, understanding. Feel free to draw the pictures on there, okay? I often do when I'm doing an air column question. I'll draw the picture of what the wave pattern looks like, okay? Things like that. Okay, I will put up a couple of the open ones here. You guys can give those a try as well. Okay, so let's say do number 9, then go back to number 5. Okay, do number 10. Just go back and forth between open and closed questions there, just so you get an even smattering of both. Okay.